Hello friends, welcome to our channel Knowledge Amplifier. So in my this particular video, I am going to discuss one very important assumption related to multiple linear regression. Okay, so in my previous video, I have discussed how you can implement multiple linear regression, what is the actual algorithm which works behind that pseudo inverse. All this I have discussed in detail. If you want to know the detailed explanation of this derivation, please go through the link given in the description, because I have already discussed, so there is no meaning in discussing those same concept again and again, right? So I have taken this particular example where x1 and x2 are my input features, okay, which should be independent, and this is my dependent or output feature, okay. And we have taken this particular equation y equal to beta naught plus beta 1 x1 plus beta 2 x2, where we need to find out beta naught, beta 1, beta 2. And by putting all these values, we got several equation, and based on that we created this matrix form, okay, where this particular matrix we termed as A, this one as X, and this one as our output B, okay. And then we have derived considering Ax equal to B, how to find out the X, because our ultimate aim is finding the coefficients beta naught, beta 1 and beta 2, right? And we have came up with this particular equation, X equal to A transpose A whole inverse multiplied by A transpose multiplied by B, where B is basically my output feature and A is basically my input feature, column wise written with the first column as all ones, right? Now there is one concept which you must consider while applying multiple linear regression, and that is multicollinearity. What is that? Multicollinearity means independent variable is a perfect linear combination of one or more than one, okay, other independent variables, right? I am repeating again. One particular independent variable is perfect linear combination of one or more than one other independent variables present in my input feature, okay. This is called multicollinearity. And how this particular thing is important in the multiple linear regression point of view, I will be discussing. But before going to multicollinearity, just have a quick recall of one particular concept which you have already studied in your applied linear algebra course in BTech, right? So what is that? Just consider one simple example. A equal to first column 1 2, second column 3 4. See, here perfect multicollinearity is present. Why? See, suppose this is one column, one feature, this is another column, another input feature, okay. Now see, second column is basically linearly dependent on first column. You multiply 3 with the first column, you will be getting second column. So here multicollinearity is present, yes, because the definition is satisfied. One independent variable or input feature is perfect linear function or linear combination of one or more than one, in this case one independent another independent variable, which is this one, right? So here multicollinearity is present, and if multicollinearity is present, this perfect multicollinearity, okay, one particular column is a linear function of or linear combination of other independent columns, that times what happens? See, there exists one X where X not equal to 0, for which we will be getting Ax equal to 0 if this type of cases appears, right? See, very simple. Consider, suppose my X is 3 minus 1, this column matrix, and you see what will happen. You just do this multiplication, 3 into 1 plus 3 into minus 1, that will result into 3 minus 3 plus 3 into 2 plus 6 into minus 1, that is 6 minus 6. So 3 minus 3 plus 6 minus 6, which will result to 0, right? So what we are concluding, in this case Ax equal to 0 possible where X not equal to 0, because you can see 3 minus 1, this column, this matrix is not equal to not 0 matrix, right? So if Ax equal to 0 happens, for which X, this particular one, not equal to 0, then what might happen further? Suppose, okay, suppose for this particular A matrix inverse exists, okay, and suppose that is A inverse. Now you multiply A inverse both sides. What you will be getting? A inverse Ax equal to A inverse 0. A inverse 0 is what? 0. and A inverse A is what? Inverse multiplied by that matrix should be identity matrix, right? And identity matrix multiplied by X should be X only. So we will be getting X equal to 0. Point to be noted, what is X? X is 3 minus 1. So 3 minus 1 equal to 0. Is it possible? No, it is not possible. So what is the conclusion? That A inverse does not exist. Okay. See, simply I have derived one very important conclusion. Ax equal to 0 for considering this particular A matrix, okay, and we are taking X as this one only, 3 minus 1. We are getting Ax equal to 0, right? Here we have seen. Now suppose A inverse exists, then what we are getting? Multiplying A inverse both sides, we are getting X equal to 0. But X is non-zero, it is 3 minus 1. So 3 minus 1 equal to 0. This is not at all possible with respect to practical real world point of view. Okay? Absurd thing. So A inverse actually does not exist for this particular matrix. So in general, if we generalize this particular concept here, just I have shown with one example. If we generalize this one, suppose one particular matrix has these columns x1, x2 dot up to xn. Okay, these are individual columns and my whole matrix is X, capital X, and I am having one C, okay, which is one column matrix like this one, okay, C1, C2 up to Cn. If you multiply this matrix with this matrix, what you will be getting? See, C1 x1 plus C2 x2 plus C3 x3 dot plus Cn xn, that is this one. Now when we say x1 x2, that is these individual columns are linearly independent, when this particular one C1 x1 plus C2 x2 dot plus Cn xn equal to 0, if and only if C1 equal to C2 equal to Cn equal to 0, that is all the these values should be 0, that is C matrix should be 0, and then only this particular X into C becomes 0. That time we will conclude that this x1, x2, all the individual columns of my X matrix are linearly independent, and that's what the definition of linear independence. But suppose one particular column, okay, in my this X matrix is linear function of one or more than one other columns, that time what will happen? X multiplied by C equal to 0 for C not equal to 0. Okay, like here we have seen that these two columns are dependent, okay, linearly dependent, and we are getting such X which is basically not equal to 0, for which we are getting Ax equal to 0, right? So, and this is obvious, this is the definition of linear dependence, linear independence, nothing new I am talking, this is all we have studied in linear algebra also, right? So if these individual columns x1, x2 up to xn are linearly dependent, then we will be getting C1 x1 plus C2 x2 dot plus Cn xn equal to 0, where C not equal to 0, that is all the values will not be simultaneously 0, okay, that is C not equal to 0 if x1, x2 individual are linearly dependent. Okay, so now see, if C not equal to 0, again we can generalize the same concept whatever I have discussed here, that X is one matrix where X equal to 0, okay, for C some C not equal to 0, then if X inverse exists, then we should get this one X inverse X equal to 0, X inverse X, okay, should be identity matrix multiplied by C should be 0, so C equal to 0. Here we have assumed C not equal to 0, but here we are getting C equal to 0. Together simultaneously not possible. So here this assumption, that is X inverse exists, this is wrong. Okay. So the conclusion is, if one column linear function of one or more than one other columns of a particular matrix, then for that matrix inverse does not exist, and that type of matrix we call non-invertible or singular matrix. Okay, remember this. Okay, so the conclusion what we have achieved, I have written here, if it has linear dependent columns, that time there exists an X which is not equal to 0, so that Ax equal to 0. Okay, right? And for the same this X only which is not equal to 0, if we just multiply both sides transpose, A transpose Ax equal to A transpose 0, which we can get as A transpose AX equal to 0. Suppose A transpose A you can consider as B. Okay, so we are getting here Bx equal to 0. Now see, Bx equal to 0 where X is non-zero, right? We have seen here X is non-zero. So what we can conclude, Bx equal to 0, X is non-zero. That means the some columns of B matrix are linearly dependent, and linearly dependent means what? Inverse does not exist, and here B is nothing but A transpose A, right? So the conclusion is A transpose A also going to be singular matrix, okay, or non-invertible matrix. So the conclusion what we have achieved is, if A has linear dependent columns, that means if multicollinearity exists, okay, perfect multicollinearity, that means if one particular independent column can be represented or is linear function of one or more than one other independent or input columns, that time A transpose A is going to be singular. And what we have got the formula for multiple linear regression, if you see, A transpose A whole inverse. Now the conclusion is, if A has linear dependent columns, that time A transpose A is non-invertible or singular, or inverse does not exist. So we cannot calculate the coefficients. Okay, very important conclusion. That is, this particular one will not at all valid if A matrix has linearly dependent columns. Okay, so the assumption for multiple linear regression is no perfect multicollinearity. Okay, no perfect linear relationship between input features, okay, or independent variables, whatever are columns of my A matrix, whatever are input features of my data set. Remember this, right? Because if perfect multicollinearity or linear dependency is present, that time A transpose A will be non-invertible. That time we cannot calculate this particular expression. Okay, so for multiple linear regression, one of the most important assumption is no perfect multicollinearity, right? That is, one particular input feature or explanatory variable cannot be linear function of one or more than one other independent or explanatory variables present in our dataset, right? I hope you have understood this particular assumption. This is all for this video. Thank you for watching.